All right, 10 more minutes and we'll start. How many of you got a chance to read the paper?
I tried reading Asif, but it's a little too terse. So I kind of read a couple of pages, but then kind of left it. Couldn't wrap my head around the overall concept. So made an attempt.
Nice. Anybody else? Pradeep? Did you read this?
No, sir. I was preparing for exam next week as final exam. So
Oh, have your final exams, right?
yes.
And I can follow the intuition, what they're saying, but how they're building it up is, I'll rather listen to you.
Okay. All right, we are on time. We have more people join there, right? So I'll just start. This paper just came out, I would say, a week or two ago. It's a very interesting paper. Usually, I don't give papers that come out that are absolutely fresh. We have been covering the classics in some sense, the big papers, the bird, the attention is all you need, and a variety of other papers which are very important, considered in some sense landmark papers and well established. Today, I'm going to cover a different paper which is just come out. We do not know how much impact it will have, but it certainly makes some very strong points. It belongs to a line of investigation that people are pursuing fairly vigorously these days that tries to understand what exactly is a neural network doing. When we take a neural network, and it has lots of layers in it, a deep neural network, you have enormous amount of parameters. These days, have 100 million, 500 million, or billion parameters, or even 100 billion, 200 billion parameters is considered pretty like normal. We have reached a stage at which neural networks are so big, it is very hard to impose interpretability on it and see what is it doing. So what we do is we apply interpretability by different means, like we make approximate models to mimic its behavior in local regions of the feature space. We do things like that. But we have no direct way to just layer by layer see what it is doing. Our current understanding is that and it sort of is motivated by convolutional neural networks. We see that each of the convolutional neural net, what it does is layer by layer, it seems to do feature extraction. Right? In the early layers, you have the primitives, geometric primitives, the edges and things like that being extracted. And then higher order representations are gradually built out of those primitives. Right. So the current understanding is deep neural networks work through representation learning or some sort of a hierarchical learning. As you go deeper and deeper into the network, the next layer builds upon the representations that the previous layer has learned, which is very good, but we seem to have hit a little bit of a wall. It doesn't further interpretability beyond that. So a lot of people are very seriously looking at the deep neural network and asking, can we look at it from a different perspective? Can we reorient the way we understand this whole thing? Perhaps in such a way that it becomes easier for us to get grasp what is happening inside. And if we can grasp what is happening inside, perhaps we can accelerate the pace of research in deep neural networks. As you know, we are making a lot of incremental progress, wonderful incremental progress, though some people believe that we are not making fundamental breakthroughs, including Jeffrey Hinton himself, who seems to believe that we have hit a wall. And so obviously there is a need for more work and more theoretical breakthroughs to further or take things further. I consider this paper interesting. At this moment, I suppose the research community will gradually weigh in on this paper and we'll see how much impact it has. But I thought it was interesting, certainly. What question? Make some very good points. We are going to take this paper, dissect it, see what it says. It's fortunately a set of very simple statements it makes, but very insightfully it makes those statements. So let us pursue the reasoning that is there in these papers. Now, in this particular paper, the title itself is quite provocative. It says that every model learned by gradient descent is approximately a kernel machine. Now, let us limit ourselves to deep neural networks for the time being. In deep neural networks, if you remember, deep network or deep learning, essentially the pillars of our progress have been, the basic ideas have been that you do forward compute, two, you do backward propagation of gradient computes, right? Basically, gradient of the loss with respect to the weights of each of the layers. If you keep on back propagating it layer by layer. And then the third step you do is the gradient descent. Where you essentially say the next value of the weight of any weight vector is essentially the current value of the weight vector minus the learning rate. Typically, we use alpha, and then right, we take the learning step. So I hope this part is pretty well established in our minds now, that the forward pass is just matrix multiplication. Simply matrix maths and activations. And activations at each layer. So these are the three steps of a deep neural network training. Right? Training is, and of course, evaluation is just eval is just the first step after the weights have been trained. Now, I will just, so the crucial thing here is to note that, of course, we do gradient descent. This is what we do. We do all sorts of gradient descents. We do batch gradient descent, stochastic gradient descent, momentum-based gradient descent methods, add-on, this and that, and so forth. Right? So, but ultimately, we do gradient descent. Right? And gradient descents are considered first-order methods because this is a first-order derivative of the loss. Right? So just to recap, L is the loss function. Right? It is some function of y and the gap between y and y hat. Right? So for example, a loss function could be y minus y hat squared. Right? Suppose I do this. This would be a sort of a sum squared loss, and if you divide by this, it is a MSE. Mean squared loss. So there are many loss functions. You can have cross entropy loss. laws, and so on and so forth, classification, regression, and you can cook up a more interesting loss functions. But invariant to which loss function you do, at the end of it, it is back propagation of the gradient computes, and then you do the gradient descent step. You actually take the gradient descent step. Right? Now, coming back to this paper, what is noteworthy is it says every model learned by gradient descent. Right? So that's a pretty general statement. It's saying that not just deep neural networks, but just about every model that you learn by this process is approximately a kernel machine. Right? Now, let us recap what are kernel machines. Kernel machines is a synonym for or also called support vector machines. Right. Let us recap what they are for a moment. And but before we recap, just observe what the title is saying. It's saying something quite profound. It is saying, in a sense, that if you are doing gradient descent in your model, you are basically some form of a support vector machine or a kernel machine, right, approximately. And I would say that that's quite a startling statement to make. Let us see how they go about proving it. It turns out that they prove it in a fairly mathematically rigorous way, and we need to walk through this. So what are kernel machines? Suppose you have a very intuitive picture, and this is an extremely quick recap that I would give is, kernel machines try to find a target, a space, a kernel space where every data is linearized. So for example, if you have points, let's say that you had a data like this. And data here showed up as, let me say, a decision boundary really was like this. Right? And let us say that you had points like this. And let's say I'll put green points here. This region is green. Let's throw in a few mistakes. And a few mistakes for yellow too, maybe. Something like this. If this is your decision boundary, what kernel machines try to do is they try to find a space where the separation could be something. Let's say that it becomes a straight line, like say, can I bring a ruler here? Okay. Let me see if I could. All right, let's bring it here. Much better. And we don't need the ruler. So let us say that it becomes something like this. And it becomes a linear decision boundary with its with its margin. There's a maximal margin hyperplane and all of that theory. We won't go into that. So in other words, if you remember, the intuition we used is how can we straighten the river and flow the widest river through data in the kernel space. Now for each point x, if you remember, we assume that there is a mapping function. There is a mapping function that takes it to a point, this from here, that is the phi of x. Do we remember this, guys? That we need a function, a mapping function to a different kernel space where x goes to phi of x. Then we say that the beauty of this is kernel trick says we don't actually have to compute phi. We can get away, but what we need to do are find support vectors, which is that these certain lighthouses that can guide or define the decision boundary. So for example, you may pick up some lighthouses, maybe this, right? Or this, and a few lighthouses or support vectors that help define the decision boundary. They clearly help define the decision boundary. And all you need to do is, given a sample point, given a query point, point X, an arbitrary query point, if you want to decide whether it is yellow or green, all you need to do is find the similarity of this point with respect to every these lighthouse points, these 4 lighthouse points, let me just call it K lighthouse points. If you can figure it out, what is the similarity of this, or how close is this point in the kernel space to a few lighthouses, you will be able to tell. For example, if your point X is here, let's say it is this, you will agree that it shows that if I can relate it to these points, and I can basically come up with a way to tell that it should be yellow, right, based on certain things. So obviously I'm using hand-waving arguments. I don't want to go into the whole mathematics that we went into. Now, what is the similarity in the feature space? Similarity in the kernel space. Now, if you remember, this we realize is the dot product of the feature vector, this, and the xi, and these are the 2 vectors. We define the similarity as simply the dot product, which is the most intuitive notion of similarity. So we are looking at the dot product of these 2 points in the kernel space, and that's a measure of similarity, right? And the whole point of support vector machines or kernel machines is perhaps you don't need to do that for all the points in your training data, but you can handpick a few, the so-called support vectors, you make them into lighthouses, and quite often they are enough to guide you through, right? In the worst case, all your training data can become sample or lighthouses or support vectors. So this is your essential theory of support vector machines.
So Asif, just so that we can understand that concept clearly, right? The concept of the lighthouses. So I have not done support vectors earlier. So that's I'm trying to kind of get a intuitive sense for it right now in this conversation, right? So that the lighthouse or the support vectors that you mentioned, are they necessarily around the boundary line?
They are.
And the proximity to one or the other tells you which side of the boundary line you are on. Is that the intuition?
Somewhat similar, yes, that is the intuition. You can take that to be roughly the intuition.
Okay.
So that is that. So there are 2 steps to it. You need a kernel mapping function, what you call the mapping function. And you need a kernel function. So these are called kernel functions. Kernel function. And it's to be distinguished between the mapping function itself. And using these 2 things, actually, the entire theory of kernel methods is developed. And it's a very rich literature that we have here. It's a whole world in itself, just like deep learning is a whole world in itself. If I were teaching the same workshop, let us say 15 years ago, then I would be giving a long 4 months workshop on just kernel methods. But at this moment, we are going to limit ourselves with just this very basic explanation. Now, those of you who have taken support vector machines or things like that in the previous workshop with me, do you guys remember what I'm saying? Any one of you would like to confirm?
Yeah.
Yes, yes, Asif.
So the idea is that when you use this,
So that's the maximum margin classifier.
exactly, the widest river or the maximum, technical word would be maximal margin. And I've tried as much as possible to make it intuitive in terms of real things that we see, rivers and so forth. But that's what it is.
Asif, can you hear me?
Yeah.
These terms that you use, I had this question when I did the session on support vector machines. Also, the lighthouses, are these sort of the common terms used to explain?
No, I use those terms.
You use okay.
I flow rivers and put lighthouses on their banks.
Okay, all right.
You won't find this in the literature. The literature is more abstract.
Right? Yeah, it clearly explains the concept and gives the intuition. But I was just wondering, these are your own terms.
These are my interpretations to explain these things. So you won't find it elsewhere. So now
the kernel space is always a higher dimensional space, right, compared to the space that you started with, correct?
not necessarily. I'll give you a counterexample. Huh? So let me pose this question here as part of our note so that you have it. The question is, are kernel spaces always higher dimensional spaces, right, compared to the input dimension, right? Input
Yes.
dimension. This is the equation. So I'll give you a counterexample that will hopefully, but broadly speaking, yes, it is true, but there is a counter. I can give you very quickly a counterexample. So let's say that you are looking at data which happens to be in this circle. And from the circle, you can generalize to an ellipse or go to a higher dimension to a sphere or an ellipsoid. But let's keep our discussion simple. Suppose data points are here. Right? And the green data points are, actually, let me not use plus, they look like crosses. Let me use something like this, right? And we can throw in a few mistakes here and there, error points. Let's throw in some noise here. Throw in a couple of noise points here. Okay. Nice points, and we'll throw in a few yellow points outside also. Sorry, crosses outside also, for what it is worth. So now you look at this problem, and certainly the decision boundary. What is the decision boundary here? It is this guy. So the decision boundary looks circular. Circular, right? In other words, nonlinear. Right here, we got that. Now we ask this question. That was Aditya speaking, isn't it?
Yes, yes.
So I guess I recognize your voice. So now imagine that I do one transformation, x, let me call this axis x1, x2. So suppose x1, x2 goes to this mapping function, which converts it to x1 square and x2 square. As simple as that, right? And see what this transformation does to the data. Now my new axes are, let me call it is equal to the phi x1, phi x2, right? So in this phi1, phi2 space, each of these points when you put, you will realize that, see, what is the constraint equation here? X1 square plus x2 square is equal to 1, or some value, some radius. I'll just take, maybe, why take 1? Let's be r squared, some r squared. Would you agree that this is the constraint equation for the surface?
Yes.
Right, for the circle rather. We all know that this is the equation for the circle. Now what happens in this space, this is phi x1. This is phi, the x2, phi, so this is phi 1 rather. Let me just phi 1 of x, phi 1, let me just write phi 1, phi 2, phi 2. Would you agree that this would become this, right? Let me write it here because that will illustrate the point. Phi 1 plus phi 2 is equal to a constant r squared. This is the constraint surface now, right here. Now, what is this equation about? This equation is actually a line that goes like this, right? This is the line for phi 1, phi 2 is equal to phi 2 is equal to r squared. You can convince yourself, right? So when phi 2 is 0, this much is r squared. And when phi 1 is 0, this much is r squared. And now all your points go here. And all your green points are outside. So you have gone to a space which is linear, but what's the dimensionality of this space right here?
This is like linear.
Yeah, but the dimensions. This one is R2, a
Yeah,
two Euclidean space. This one here, and this is also two-dimensional Euclidean space, isn't it?
yes.
Just a plane. So, in other words, when you go from here to here using the phi mapping, it is not necessarily true that you have to go to a higher dimension. Sometimes you don't need to go to a higher dimension. You can stay in the same dimension, but you just need the right transformation.
Okay. But it never go to a lower dimension, right? It can be either same or higher dimension.
Yes, usually, I mean, you don't see it go to lower dimension. See, in practical terms, what happens, right? You use the Gaussian kernel and such things. If you remember, the RBF kernel or the Gaussian kernel, they go straight away to infinite dimensional Hilbertian space. If you remember from the last time, we go from any problem, we take it to infinite dimensional Hilbertian space. Hilbertian space. Hilbert space or Hilbertian space. No. Because everything is expanded in terms of infinitely many Gaussians, if you remember. So that much you might be not remembering, that got technical by the end of the support vector machine. So in practice, what people do is they directly go and launch it to a high space and figure it out. But at least in the theory, you don't need to go to a higher space.
Okay.
So this was our basic thing. So now again, I'll end it with one basic intuition, kx. If I have given a query point, a probe, an xi, and a data point, so we'll use this word for query or probe. Query point, data point, and this is the probe, this is the actual data point in training data. We'll use that. And what we are seeing is it is the dot product of phi x and phi xi, the data point. So how similar this point is depends upon a kernel function, which is nothing but the dot product in some kernel space. Some kernel space. And that is the one important thing to carry forward in this paper. With that being there, you say, and there's a little bit more, you say that y, remember it's a linear equation, right? So y can be written as The out can be written as basically in terms of the kernel. So you take the kernel functions x and xi, all the points in the training example, right? And what you do is, this is the point that I'm going to mention to you. You take a linear combination of these, linear. So this is a linear combination of all the similarities. Add a bias term also for what it is worth, b, and then sum over, I mean, linear combination would imply this. So in other words, it will be like a1 kx x1 plus a2 kx x2 in the data point all the way to b. Are we together? It will be like this. And there is one more thing that you have is that given this, you may also apply a non-linearity function, an activation function to it. I'll just write it as G because the paper writes it as G. A non function overall. And you can say that Y is equal to this. Right? So it is the linear superposition of the similarities to each of the data points and throw in a bias term if you want, and then if needed, apply a nonlinear activation function. So that is what is being said here in this particular equation. Let me mark this. So this equation now hopefully makes sense to you. So with that background, let us go and read this paper from the very beginning. I will read out the abstract. This abstract is
Asif sir, can you increase the resolution? Yeah.
I am doing that. That's exactly what I'm doing. Give me a second. Much better?
Yes.
Okay. So it goes on, it says, and so first of all, I always like to go straight to the keywords. What are the keywords here? So you'll be talking about gradient descent. We'll be talking about, let me make the fonts a bit, either print is smaller. Kernel machines or support vector machines. Deep learning, so it will limit itself to deep learning. Our current understanding of deep learning is representation learning. And now comes a new concept, which I'll explain, the neural tangent kernel. So this is of growing interest. In research these days. People are taking this quite seriously and paying attention to it to see what all things it is saying. Right. So these are the keywords. You know every one of them except the neural tangent kernel. I hope. Now let's start reading the paper. Deep learning successes are often attributed to its ability to automatically discover new representations of the data rather than relying on handcrafted features like other learning methods. In a sense, the power of deep learning was that you didn't have to do a lot of feature engineering. The idea was that hierarchically, layer by layer, it would discover the feature on its own. Isn't it, guys? Right? So any doubt in the first sentence? We show, however, that deep networks learned by the standard gradient descent algorithm are in fact mathematically approximately equal to kernel machines. So that is sort of the important feature, I suppose, that we are talking about here. Let me take this itself. We show this sentence is the most important sentence, these two. It is just one sentence. I'll repeat it again. We show, however, that deep networks learned by the standard gradient descent algorithm are in fact mathematically approximately equivalent to kernel machines or support vector machines. A learning method that simply memorizes the data and uses it directly for prediction via a similarity function. So Do we understand what he's basically saying? He's alluding to the fact that we need to just pick out a few lighthouses and remember them. And once we have a similarity function or the kernel function, then that's all we need. Given that kernel function and given a few support vector machines, we can solve the problem, right? We can do classification, regression, whatever. Let's take classification. We can do that. Is that easy now, intuitive, guys?
So Asif, like, what does this memory exactly means? Like, is it if you memorize, like, is that not like overfitting?
No, the problem is if you memorize it, you can only respond to data points that you have seen. The point of support vector machines is it sort of remembers a few instances, the support vectors of the lighthouses. It memorizes only a small bits, and then it uses to generalize from there. In fact, support vector machines are very robust to overfitting because they memorize only a few data points. They discover the real gold, the real ones that matter in the data, and light them up as lighthouses in effect, make them into support vectors and use them. That's how the support vector algorithm works. So it's sort of
Oh, okay.
a broad.
So is it like in essence like a generative model, right? Like, so based on few points, I can generate and get like something else.
Not a discriminative model, but given a few points, I am able to do the classification for any point, right? For any point
Okay.
feature space, I'm able to do the classification. Still discriminative, but yes.
Okay, yeah.
So Asif, a quick question here. Why wouldn't you use the word centroid for the support vectors?
Because there's no relationship of centroid to support vectors.
Is it not the, like, if it's trying to distinguish between two spaces, aren't these support vectors in effect finding the centroid of the space? That's
No,
not it.
they are not. I think
They're not.
so
Okay.
anyway, you have to sort of go through that class, the ML200.
Okay.
Because we developed the support vector theory in great detail. And it's too little a time now to cover the ground, but suffices to say it is not based on the centroid idea.
No, the difficulty I'm having is trying to, if something is on the boundary, it is closer to the other side as well.
That is true.
So me trying to find a cosine similarity with something at the boundary could easily be, when the cosine similarity of something on this side of the boundary would be the same as something on the other side of the boundary, correct?
See, here's the thing. Suppose I'm looking at a point like this, right? This point. Now, if you look at this point, what you do is you do the kernel with respect to all the points. But what will happen is the similarity between these points will dominate. On this side will dominate. And what they will do, because they dominate, the overall sign of your y, the sign of y, which is with the sign as sign as in symbol, plus or minus, -1 or +1, it will tend towards, let's say that this side is positive and this side is negative, right? So actually, usually people mention it the other way around, minus and positive. So what will happen is it will tend, the value of y will tend towards negative. It does not deal with similarity. You are doing the function, you are still doing AI kernel with respect to all the four. Like for example, here there are 4 points. So you are doing with this point and xi, you're doing the similarity with respect to each of the 4 lighthouses. But the net result would be, and I'm just removing the non-linearity transform. The end result of this would be, and let me throw in a bias term, end result of this is this will still come out negative. And so you would know that it's a yellow point.
Okay. So in essence, these sample points or these subset of points that the support vector algorithm is able to bubble up are salient representation of that set.
Yes. That is it. The whole point is that it discovers which points are the most essential in this whole story that help explain the rest of the data.
Okay.
So now the next sentence that is here. So guys, I'll reread the most crucial statement. We show, however, that deep networks learned by the standard gradient descent algorithm are in fact mathematically approximately equivalent to kernel machines, a learning method that simply memorizes the data and uses it directly for predicting via a similarity function. Right? So the whole question then is, excuse me, what is the value of this? So the value of this is this greatly enhances the interpretability of deep network weights. You know, these weights that we have, it gives a lot of interpretability to it, or to the parameters. It elucidates, by elucidating that they are effectively a superposition of training examples. So, you know, if you realize that the weights are nothing but superposition of the training examples, what they do therefore is somehow they encode the essence of the data that they have seen in some sense, right? They extract the essence of the data in many ways. So that is that. The network architecture incorporates knowledge of the target function into the kernel. What is a target function? At the end of it, a neural network is nothing but given x goes in, it is y of x, isn't it? It is, or another way of writing it is y is some function of x with respect to the weights of the model. Right? This is, at the end of it, if you look at it as a box, this is what a neural network is. Would you agree, guys? Right? No, not only a neural network, every single thing, every parametric model is essentially something like that. It is some function of the input. The only question is we don't know what function. We expect it to be a differentiable function, so on and so forth. We impose good qualities upon it, but it is. So that's your target function, the target. And so they go on to say that this improves understanding. This improved understanding should lead to better learning algorithms. So the hope is that because now you understand or have better intuition into what is going on, it will accelerate some of the developments coming. So despite its many successes, deep learning remains poorly understood, which is true. In contrast, kernel machines are based on well-developed mathematical theory, but their empirical performance generally lags behind that of deep networks. Yeah. So today, what happens is the kernels that we were using in support vector machines, the RBF kernels, the polynomial, the linear kernels, if you use those kernels, the kernel machine performance is below that of using a deep neural network, for example, a CNN for image classification. So that has been established fact, right? That is why support vector machines at one time were the king of MNIST or digit classification and so forth. But today, deep neural networks have taken over, right? So we have this dilemma. Kernel machines are very well understood. They're very intuitive. But deep neural networks are not really understood at all, much at all, but they give you superior performance, right? And that's why people sometimes say that maybe this new genre of algorithms cannot be interpreted and all sorts of nonsensical statements. So anyway, we'll move forward with that. The standard algorithm for learning deep networks and many other models is gradient descent. Here we show that every model learned by this, regardless of architecture, is approximately equivalent to a kernel machine with a particular type of kernel. Right? And then you go on to say many more things, but I will now go to the meat of the matter. So this is a kernel machine, the basic equation of a kernel machine, which says that the y can be computed by looking at the similarity of a probe point. So given a probe point, query point x, and you're trying to find the y, all you do is look at its kernel similarity to a bunch of lighthouses, to a bunch of, in the limit, you can find its similarity to all the points, all the training points, and take a linear superposition of them or linear combination of them. And that is it. If you need to throw in a non-linearity, you can throw it in. But that's about it, right? Into this argument. So Now, what happens is that this AI, the coefficients of the similarity are typically functions of the labels itself, plus, minus, and so on and so forth, the 1, -1. Kernel machines, also known as support vector machines, are one of the most developed and widely used machine learning methods. Right? So the point that is that they are very well understood. We know the entire books written about the mathematics of support vector machines. Right? Mathematicians have really gone at it and made it on very solid foundations. So in the last decade, however, they've been eclipsed by neural networks and multi-layer perceptrons and so forth. And people used to believe that kernel machines can be viewed as neural networks with just one hidden layer, with the kernel as the nonlinearity. Right? But now these guys are going to make a different statement. So we'll watch out for that. This equation, guys, is what is it? This is our gradient descent. We would have written it as W next is equal to W minus alpha gradient, the loss of the weight. Is this true? We would have, and this is implicit, so I won't write this. This is the way we write it, isn't it? So what it means is that this is the same as this. In this paper, they use the word epsilon for the learning rate. So that is all right. Now comes the big result that they're going to show. The result that they show, and in the rest of the paper, they prove it, is that you're looking for that similarity function between the query point x and each of the, let's say, some other point x prime, and typically the other point is a data point in the training data. It says that that thing is actually nothing but the gradient flows. Right? The word people often use is the kernel. These are the tangent gradients, or the tangent gradients are being used. So we will go over it in a more specific way. So I will read it from here. Specifically, the kernel machines that result from gradient descent use what we term a kernel path. If we take the learning rate to be infinitesimally small, the path integral between two data points is simply the integral of the dot product of the model's gradients at the 2 points where the path, over the path taken by the parameters during gradient descent. Right? So what happens is that, suppose x, if you take, so when you do gradient descent, w, the weight vector, it will go from this to some other point, W final, right? So this is a very non-linear. It will shift to this place in the feature space, in the parameter space. Let's say this is your W space, right? If you think of it, this is your 100 billion or 100 million dimension space or whatever. But for simplicity, assume it's a 2-dimension space. So your weights, guys, excuse me for a moment. All right. So, you can think of your parameters. It's much easier to think of it in 2 dimensions. So what happens? As the gradient descent happens, your weights will take some path, they'll go along certain values. Any one of the weights will shift a little in small increments at each step of the gradient descent. So what we are saying is, if you look at how the response changes, y changes with respect to the weight, right? That is the most important thing. And it turns out that if you look at this is again a dot product, guys. Do you see a dot product inside? That dot product immediately gives you a sense that we are getting close to the notion of similarity here. Specifically, the kernel machines that result from gradient descent use what we term as a path kernel. So this is the path. And what we are saying is that this point, let's go, let me draw it out here. Again, I'll sort of let me bring that equation down here. Okay, this is very illustrative. If you look at this, you started out at this point, and W final, after a few steps of gradient descent, it has gone from W1 to W2, W0 to W1 to W2, right, to W3 here, W3 here, to finally W final, right? This is the path that the weights have taken as the gradient descent happens step by step. So at each point, what you can compute is that y is the output. You know that the black box is essentially x goes in and y comes out, right? So what you can do is at each point, you can compute, and it is a function of the weights. Right? There is some function, y is some function. You realize that it is a function, some function of weights, and of course x. So you can take the gradient of y with respect to the weights. How much does y change? If I just change the weight a little bit, how much does the output change? Right? That sensitivity of the output to changes in weight is given by grad y, right? Y of x. So at each of these points, W0, etc., you can compute the gradient. This gradient, it sort of measures the gradient. Let me give you the physical intuition here. Gradient of y, when you write that gradient of y with respect to the weight at the point x, I'll write it in words. At point x, that is the x input, with respect to the weights, the parameter weights, that is what this is. What is the intuition? Intuition is, it is the sensitivity at input x to sensitivity of the output to small changes in the input. It's not small changes in the input, I take that back. It's small changes in the parameter
Weights.
W, the weights, yeah. Excellent. to the weights, how sensitive it is. That's what gradients measure. Derivatives measure sensitivity. And now what we are saying that if you go back and look at the definition of that, this kxx prime, I'll just write it here. It is saying that the similarity of the point in the kernel space between x and another point x prime is nothing but you take a path that the weights have taken, let's say some path that the weights have taken, and this is the gradient of the weights at the of y of x, right? At this point x in the parameter space, what is the gradient, right? Dot product it, in my notation, I would write it as this, dot product it with y of x prime of the weights. So this is sort of the notation. I'm deliberately picking a notation that we are used to, right? And you compute this. So this is a dot product. A dot product is ultimately itself a function, and you compute it over this entire path. Let's say this is W naught, this is W1, this is W2, this is W3. Let's make it more, W final. So now what does it mean? Let us see what it means, right? What does it mean to take the path integral? So the explanation is very simple. Suppose you have 2 points. Let there be 2 input points, x1 and x2. These are 2 input points, right? Then you compute k here, the k. So let's go here at this point. Let's say that the gradient of this, of just an arbitrary point given a query point, think of it as any arbitrary point x, right? Which is not in the data. So remember, you have to make prediction for x. Any arbitrary point in the feature space, you have to tell whether it's a cow or a duck, for example, right? And that point is the entire, any random point in the feature space. Treat it as a query point, and you have a limited set of the data points on which you have trained your model. So let's take this. What you do is you find y of x with respect to the weight at this point. Let us say that at that point, with respect to grad y of x1 is this with respect to the weight. And let us say that the grad of this, no, I shouldn't use this. Let me use a different color. Let me say blue. Goes like this, grad w of y x2 at x2. So now look at the grad, the red vector. Which is it closer to, the yellow or the blue?
Yellow.
The yellow one, right? It's closer to the yellow one. And so you would say that here, this is much more similar. Then you can go and do the same thing here and see what values come out. Now what do? See, the integral can be also thought of as just sum or average, right? That's the intuition behind integrals. I mean, I'll just take sum. If you take discrete point integrals become sums. You go to this point now, and now I'll show you the picture that he has drawn, which is very descriptive. And let me look at this. At this point, your the y of x, the gradient of y, it is closer to x1 or x2, similar to the gradient with respect to x1 or x2?
X1.
X1. What about at the point W2?
Again X1.
Again x1. Then what about W3?
Same X1.
Same. It seems to be similar. So what you do is, I mean, obviously he has taken 3 points. An integral is nothing but the sum, of discrete points in the continuous limit. So if you keep on doing this, at the end of it, what do you conclude? This guy is more influenced by what, x1 or x2?
X1.
x1, right? It's more similar to x1. So if you look at the value that is produced, the output that's produced by x1, it will be a closer representation of the output than x2, right? And that is the main thing. It's a very simple idea, very elegant idea that they represent, right? So I'll just read out the sentence, the figure one, how the path integral measures similarity between examples in this two-dimensional illustration. As the weight follows a path on the plane during training, the model's gradient vectors on the weight plane for x1, x1, x2 vary along it. The kernel is the integral of the dot product of the gradients and this y, the x and the probe and the x1 over the path, and similarly for x2. Because on average, over the weight path, this quantity, you realize that this quantity will be greater because these two vectors are more similar along the path than this vector. Y1 is more influential or has more influence than y2 in predicting y, predicting the output for this query point, all else being equal. Huh? And that is the gist of what they're saying. Right? Now, there is a, I don't know, what is the time check? How many of you are interested in the mathematical derivation? It is 1 p.m. We are already past an hour. Let me go.
I have one question about this. So about this dot product, so it seems that you are assuming only the cosine of the angle, right? But what about the magnitude of the vector itself?
No, dot product is both magnitude sensitive also, remember.
Right.
I'm not scaling it down by the magnitudes. It is a full dot product.
Right. So for some points, it can be that even though the vectors are not similar, but magnitude wise, it can be more similar to the x2.
That is right. That is right. With a little bit of a caveat, and I'll come to that. When you work through the mathematics, right, that sort of gets taken care of. But okay. But yes, in theory, that's possible. Right? So first is we define some terms. The word the tangent kernel is it comes from previous literature. People have been researching it for quite some time, associated with the function. So this is your y. Y is equal to some function of x, which you don't know, some unknown function of x. And the parameter vector is some weight at this point, some value of the weight. And so it defines it to be the dot product. This is just a matter of definition with the gradients taken at this point. The second thing is, now that you have this definition, the integral of this, the path kernel. So given the tangent kernel, the integral of the tangent kernel over a path is the path kernel, right? This is a point. This is it. And the theorem says, suppose that you have a model like this, and it goes on to say that in the limit of very, very, very small learning rates. So learning rates tending to zero means extremely in the limit of learning rate going to zero, tending to zero. See, what happens is that this statement will come true. Y is nothing but a linear superposition of the kernels, similarities with respect to the data. And that's a profound statement. You're saying that in any method that uses gradient descent, you'll always have AI is equal to, well, profound enough. I mean, to me, it's very interesting. So it is a linear combination of the kernels, right? Or the similarities to known data points. What it means is, in some sense, a neural network develops two things: an internal memory of the data, which it encodes in the weight, and an ability to generalize from that. Right? So that's the way I see it. So now it says that this is true. Now the question is, how do we prove that this is true? The first thing is you realize that we wrote, this part is obvious, I hope. W, if W next is equal to W minus epsilon, a gradient of L, then W next minus W over epsilon is equal to minus grad, right? So that is the result they are speaking of here. This is very easy. Now what you do, and this is the part, when you take the limit of epsilon becoming very small, this is basic calculus. This becomes dw, and you treat epsilon as a variable dt. Let's say epsilon is equal to dt, a very small change of the learning rate. So for very small changes of the learning rate, the change in the weight is equal to minus, right? And so you realize that you can write it like that. Till now you have been thinking of epsilon as just a constant learning rate, but here we are flowing it. We're saying it's a variable, and for if you just look at how the weights change with respect to the loss, right? The gradient of the loss by changing small changes to the learning rate, how much does the weight change? That is proportional to or equal to the negative of the loss gradient. So that's the statement they're making. So they're converting this discrete to continuous, to a continuous statement. So this concept, this is called the gradient flow, right? This is known as the gradient flow. And there has been some literature about it for some time, right? Now comes the chain rule and the rest of it. Just observe that this statement is of course true. This is nothing but chain rule. Y is a function of the weights, right? And it is also a function of time. So if you want to, not time, t is what is mentioned here as time is actually the learning rate flow. So dy dt is, this equation is obvious, guys. This is just the chain rule, right? And so when you plug it in with this fact here into this equation, it becomes this equation, which again is very straightforward, right? This part, all you're doing is you're substituting the right-hand side from here, and it becomes this, as you can see. Well, that seems interesting enough. What about going a little bit further? So now you say that, all right, I don't want to do it directly like this. I want to say dl dwj is equal to dl partial derivative of the loss with respect to the output for each of the data sample, the sample points here, and yi d weight j, right? Which is again the chain rule of, and then of course when you do it like that, you'll have to sum over all of the i's and so forth. So this is the part. This becomes this. You can write it as this. Again, nothing but your basic calculus chain rule, and surprisingly, that's all you need to do. After that, you're looking at the result quite a bit. So when you rearrange the term, it becomes this. It's the same thing as this. Take the minus sign out, take the, just take this guy to here, and then you end up with this sort of things. Now they say that suppose, right, you apply some notational stuff, L prime is equal to dl dy, right? This part, L prime. So you have the sum over all L primes times this part. And they are saying that this part is essentially, if you look very carefully at this part, you will realize that, see this, what is this? dy dwj, dyi dwj. So it is the function of y at x. And this is the function of y at what? Yi is nothing but y xi, right? And therefore, what is this? When you do the dot product over j, this is nothing but grad of y with respect to the weight at x, dot product with grad of y with respect to the weight at x1, right? And so you have already shown that this tangent kernel is involved. And so in the limit, obviously this is a limit equation. Now, if you remove it, like if you have dy or dt is equal to something, let's say x, would you agree that dy is equal to x dt, which means that y is equal to the y previous value, y naught, right, plus x dt, except that x in our case is this minus blah, 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 right? So this equation therefore follows. Now, what is the value of this equation? It basically says that if you want to see the change of y, right? With small fluctuations, then you just have to look at that a path, sort of a kernel. Now the rest of it is, yeah, just going through more vocabulary, creating more terms. You can normalize it by multiplying by this and denominator. So this takes care of the idea of that. Remember, you were saying of the normalizing factors and so forth. In some sense, it does that. This is it. You continue here, and the rest of it is not terribly interesting. All it says is that if you can treat this is your kernel, and this part, if you write it as this, L prime, it's a matter of definition. You just define it to be L prime, right? So then your equation therefore becomes this, so long as your definition of AI is this complicated integral. That's all. It's just change of notation. But at the end of it, what you have ended up showing is that in the limit of very small learning rates, right? And surprisingly, I mean, it's not something that you would have expected suddenly, this result pops out, which says, hey, in the limit of very, very, very small learning rates being used, the output is nothing but a linear combination of similarities to input data, of training data, right? Which is quite an interesting statement that it is making. Now, there are a few remarks. It says that, remark one, so it says, the first thing it says that, see, this differs from the typical kernel machines in that AI and B depend on X, right? Nevertheless, the AIs play a role similar to the example weights in ordinary SVM, support vector machines, and the perceptron example. Examples that the loss is more sensitive to during learning have a higher weight, and so on and so forth. See, guys, this is a mathematical theorem. What it means is you cannot say that this is not correct. It is correct. In the limit of epsilon going to 0, this statement is great. So it's a mathematically rigorous proof. We can continue on with that, but let's go to the interpretation of it. What it is saying is that if 2 points, let's say that you want to find out what is the value here, y. What you do in the simplest term is, of all the input data points, see that if you change the weights, how do the weights change for this point of the loss with respect to the loss? How does the gradient flow here, and how does the gradient flow for that other point? 2 points whose gradients flow similarly, in other words, will be very close. So their outputs will also be very close. Right? That's a quite an interesting statement. Now we need to start taking seriously these gradients, tangent gradient, kernels. And that's what it says. It says that is what it is trying to find, which similarity based on those gradients, a kernel that comes from the gradients. And so the rest of the paper is quite straightforward. You get given a query, you feed in the K, the similarity to each of the data points, and then you find it out. And a linear combination of all of them, what each of them is saying, will be the answer, right? So I will reach out the conclusion. We are running out of time. So it says that even when they generalize well, deep networks often appear to memorize and replay whole training instances. As you know, see, what happens is we have known for a fact that when you train a complicated model, it does generalize, but it tends to often just, if you give it the same data as the training data, it seems to make perfect predictions quite often. It seems to have internally memorized the data. And now we begin to get an intuition of why it does that, right? Because that's what it is trying to do. The fact that deep networks are in fact kernel machines helps explain both of these observations. So what are the two observations it's explaining? Deep network weights are superpositions of training examples, applying the kernel method. No, okay. Even when they generalize, now we need to go to the previous sentence. Experimentally, deep networks and kernel machines often perform more similarly than would be expected based on their mathematical formulation. So there are a lot of people who are working very actively on this now. Now, the fact that deep networks are in fact kernel machines, basically, it turns out that they're equivalent, or they are support vector machines, helps explain both of these observations. They also shed light on the surprising brittleness of deep models, whose performance can degrade rapidly as the query point moves away from the nearest training instance. Right? So it also explains that, suppose you have trained data in one by taking data points, or training data, which occupies one part of the feature space. When you ask it to make prediction for points away from the feature space, the deep networks perform very poorly. Right. So it sort of gives you an explanation, because none of the training points are similar to it, isn't it? So now, whose performance degrade rapidly as the query points move away from the nearest training instance, since this is what is expected of kernel estimators in higher dimension spaces. It was already known for SVM. Perhaps the most significant implication of our results for deep learning is that it casts doubt on the common view that it works by automatically discovering new representations of the data, in contrast with other machine learning methods which rely on predefined features. So that's a big statement, actually. I don't know how much, what others will say about it, but to the extent they have made a pretty interesting statement. They say that we have always believed that deep networks could learn representations of the data and so on and so forth. But what they are saying is, if they are nothing but support vector machines and they look at similarities, they pick those crucial points and look at the similarity of a query point to this, those data points, those lighthouses in some, or all the points, if you wish, in some kernel space. And then if that's how they work, now how do we reconcile that with our understanding that if they are representation learning engines, right? They learn higher and higher order of representation. So I'm sure there'll be more work and more discussion. We'll see what comes out. This paper just came out a week or two ago. As it turns out, deep learning also relies on such features, namely the gradients of predefined functions, and uses them. So there's gradients, right? All of these gradient descent does is select features from that. So I won't go into the rest of it. And now it will be fairly easy for you to read this paper. Most significantly, however, learning path kernel machines via gradient descent overcomes the scalability bottlenecks that have long limited the applicability of kernel methods to large data sets. So the interesting part of the breakthrough is not just for deep learning, it is also to the whole world of SVMs, kernel methods, because there the problem is the kind of kernel people were using, they did not scale well. There was the sort of the Gram matrix, which used to become very large and quadratic computations and a terrible performance. Right? SVMs became very, very slow actually for large data sets. You couldn't do. And what these people are saying is that, now they can be cross-fertilization of ideas. While you can apply kernel machines to deep learning, the other way is also true. Deep learning has developed a vast literature of findings. So if we can apply this new path kernel back to support vector machines, we can backport a lot of the results from deep neural networks back to kernel machines. Right? And that could lead to a sort of, again, a renaissance of those kernel machines over again. Essentially, that's what they are saying. Right? So they go on to say the significance of our result extends beyond deep networks and kernel machines. In its light, gradient descent can be viewed as a boosting algorithm with tangent kernel machines as the weak learners and path kernel machines as the strong learners obtained by boosting. Right? So there's more connecting into different pieces of the of machine learning and boosting and all of that. So we won't get into that. That, in a sense, is this paper, guys. Huh?
It
So
has so many things.
you understood the gist of it. It's pretty straightforward, isn't it? Any questions?
It has, I mean, the understanding, the main core understanding is simple. Intuition is simple, but it does, like, they make a very important observation, multiple important observation.
Right. And the derivation is so easy, isn't it?
Right. Yeah, very straightforward.
Yeah.
But if it does, I mean, if all their observations are true, it will, probably lead to a lot of convergence between
And
traditional classical and the deep learning.
that is true. Actually, this is all very recent work that I have been observing happen. If you keep following the archive and you see what papers are coming up, they're getting a lot of attention. By the way, this paper is getting a lot of attention. The tangent kernels, no, this which is the dot product of this gradients with respect to weight at points, which are called tangent kernels, they're getting a lot of attention these days from a group of researchers. So let's see what comes out of that, but it's certainly being taken quite seriously. So guys, this was a theoretical paper. We have been doing a lot of practical papers, the birds and this and that. I thought it may be interesting to take a deeper dive into how people are researching and thinking about the foundations of deep learning. Any other questions, guys? That's all I have for today.
Sir, one more thing, sir. It looks like the, the debate between the classical method and the deep learning will continue to go on multiple parameters like computation and the understanding, interpretability and so on.
Right. See, to know that something that looked exotic, right, completely different, you can actually see it from familiar perspective itself is a big thing to see them as kernel machines, which are so well understood. I think it furthers the understanding of deep neural network. And the other way around, the fact that deep neural network has made such wonderful progress in so many areas now means that if we could backport this path kernels, which were not used in standard SVM theory, uh, they were using very simple kernels, but if we can backport this theory back to kernel machines, there would be quite a renaissance. And so that they'll be coming together, these two approaches. Now that people realize that there's a lot of overlap between these two.
Right.
So, Asif, I don't have an understanding of SVM, just the level what you described today. But listening to the paper reading, what I'm wondering is, doesn't this pave way for more explainability for neural networks in the future?
Certainly, in fact, that is the hottest concern, and one of the hottest concerns in deep learning, the fact that we don't even ourselves understand what in the world is going on inside that box, right? And interpretability and explainability is a big deal of it. So this paper actually goes towards the interpretability of deep neural networks that we will talk about a little bit more in the regular sessions. See, most of the efforts to interpretability, they just take an empirical approach. They look at the consequence of the predictions, or they make locally approximate models, right? And in a way, they're trying to, it's almost like a blind man, and they're touching the elephants, and they're making some approximate conclusion on what the elephant looks like. And that is all very useful, and in practical terms, definitely very useful. You need to make locally approximate models and so forth. But this is more a deeper thing. It says, let's try to understand what's happening inside a neural net. And so it brings back certain degree of interpretability. So
the assumption I'm making here is with support vector machines, I'm assuming those were considered to be fully understood. The sense, once those support vectors have been identified, there is a methodical explanation for what the model is doing. Is that the correct understanding?
that is absolutely correct, actually. We do understand SVMs far better than the dynamics of neural nets. The theory is very well developed. So the one thing is that SVM sort of arose from a purely mathematical line of reasoning. There was a guy, Vladimir Bapnik, sitting in Russia. He actually developed some of the core ideas of SVMs in the 1960s, and he was completely ignored for 20, 30 years till he was rediscovered by I think some big company, AT&T, or I don't know, some company here in US, and now he's today a professor at MIT. He's quite old now, But yeah, so it started out from a very strong mathematical foundation. And that has always been the problem with SVM. People who come to the SVM theory, they know that it's very sort of interpretable, understandable, so long as you remember your vector calculus and probabilities and so forth. Because it does go into the math, like you see me, right? I go into the tangents and this and that. These are not hard, these are elementary stuff if you remember your engineering math, but if you don't, then they look hard.
I think the math part is one, Asif. What I'm trying to, when I say explainable, I'm taking it back to the business context, right? So the interpretability of the math should eventually translate to being able to explain in a business context what some of the implications are.
Certainly, yes. So it certainly moves the needle forward quite a bit, a work like this. But there's a whole slew of work going on along this direction. And interpretability of deep learning is a huge topic. Everybody seems to be trying to look at it very, very seriously.
Asif, can you explain that superposition again?
Superposition is, this is just this, right?
So that is not the memory part. Like like based on the few support vectors, it does the generalization.
Suppose you have A1 of X. Like I'll just take an example. A1 of something of P plus A2 of Q. What is this equation? It is a superposition of P and Q, with A1 and A2 as the weights. So superposition is just a term saying you take some contribution from P, some contribution for Q to produce the final results. And so with that being there, now you look at this equation. It is just a superposition of all the similarities, or a linear combination of all the similarities. That's all.
Oh, okay.
Yeah. All right, guys. Any other questions? If not, I wish you all a good afternoon. Enjoy your lunch. I'll see you tomorrow.
Right. Thank you, Asif.
Thanks, Asif.
Thank you, Asif sir.
Yes, sir.